All right, let's go and get started. Let me get the lights and whatnot adjusted. I have got the heat turning on, so I know we walked in and it was like an ice box in here, but I think we're starting to get that adjusted. Okay, just so everybody's clear on the schedule, we're here. Now it says today we're supposed to be talking about composite beams, but we talked about that last time, so today we're talking about non-symmetrical bending. And this probably isn't going to take the whole time, so we'll probably jump into some transverse shear today as well. Okay, so we're here. Your homework is due next Thursday. Homework 5, as soon as you give that to me, I'll give you a solution. We have our exam 2 review, which is on all the geometric property stuff and all the stuff associated with beams. All right? Sound good? All right. So we'll have our exam 2 review then. We'll have our exam, and then we'll get into deflections. We'll get into combined loading and more circle and columns. And then that be the semester. That is it. There is a light at the end of this tunnel, isn't it? It's happening. All right. I don't know, a little bit more on housekeeping. I don't know if anybody saw, but I posted the grades to homework 4. So that's been posted. I also have that graded for you today, as well as solutions. So let me go ahead and start to pass some of this out. Mr. Batiste. Ms. Davis. Mr. Filsinger. Mr. Fox. Mr. Gunnels. Mr. Harris. Mr. Kayua. Mr. Page. Is that the whole thing? Mr. Porter. Mr. Studer. There you go. Mr. Carter. Mr. Thompson. And Mr. Timmons. Okay. I'm not going to spend a significant amount going through this solution because I'm telling you, I got to believe this is pretty standard. I mean, you all did fairly well on this assignment, but what I did for problem 1 is I broke this up into the upper triangle, or upper rectangle, the triangle, the lower rectangle, and then the left and right hole. And what I did is a table for the x-axis moment of inertia, and then a separate table for the y-axis. So I know there's some stuff that's repeating, but in the end, I thought that would be it would make more sense. Again, I thought this was better to do in Excel just because the dimensions get a little hairy, although I think now that I look at this, yep, I got a little bit of a typo because I wrote my summary in millimeters, but this was all in millimeters. I think I copied and pasted this table from another reference. I've got inches and whatnot, but it's all millimeters, so sorry about that. But in the end, all the calcs are fine. And then here's the shear and moment diagrams. Here's the one for problem 1, there's the one for problem 2, and then there's the one for problem 3. I think in the end this was pretty straightforward. So I know my structural analysis folks are probably getting a little tired of this stuff at this point, but can't be said they didn't learn how to draw a shear and moment diagram at Marshall. I can tell you that for a fact. It's been drilled into their head. Okay, any questions? All right, let me pass this out so you all have that. Apologies for that typo on the first page. It's all millimeters. So 1, 2, 3, 4. 1, 2, 3, 4, 5. There we go. I guess everybody must be still in, or we must have some folks who are still in emotional adjustment after the debate last night. Missing a number of folks, so maybe that's what it is. It's funny, I teach on Tuesday nights, so we're going to be teaching and having lecture during the results. So I'm sure everybody's going to be checking their phone going, uh-oh,
Just cancel.
Yeah, that's a good excuse. I don't really care about the debate with that, but cancel class.
Well, what I will say is this. I'm not canceling class. Marshall's open. But if you come to me and you tell me that there is absolutely no way, shape, or form, and show me your schedule that says this is the only time that I can legitimately go vote. In other words, like my Tuesday schedule is blocked and you need to take 15, 20 minutes to go vote, I'm fine with that. So. Well, but it doesn't take an hour and a half. Well, that's what I'm saying, though. If you can demonstrate to me that your schedule is such that you have no other time, then take 15, 20 minutes and go vote. I'm serious. So, all right. Far be it from me to stand in front of your civic duty. Okay. Before we get into the lecture, one thing I do want to point out to everybody. The SAME ASC student chapter is organizing a tour of the Bluestone Dam in November. That's in Hinton. It'll be on Friday, November 4th. There's going to be some carpooling to get there, but because it's a dam and whatnot, and because it's managed by the Army Corps and whatnot, they need your information as soon as possible. So if you're interested, email your full legal name to this address. He's a student who works at the Corps, and he's been organizing the tour. And the thing about this is one of those things where, if you kind of want to go, but you're not 100% sure if you can go, still go ahead and put your name on the list. It's easier to put your name on the list and then drop out than 3 weeks down the line go, I think I'm going to go. No, that isn't going to work. Okay, so if you're interested, there you go. All right. Sound good? Okay. All right. So let's go ahead and get back into the material. Let me get the sign-in sheet and whatnot passed around. Now, here's if you could date that for me. Okay. So last time what we talked about was this, and we spent a lot of time talking about this, the concept of composite bending. And this is I think what you found when you got into this is actually kind of an involved example, because there's a lot of stuff you got to figure out. You got to figure out, does the beam govern the behavior? Do the plates govern the behavior? How much moment can be resisted by the beam by itself or the beam plus the plates? And there's a lot going into it. I guess for lack of a better term, we really dug into the bending stress formula last time. And we really got involved with the mechanics. That's why I really like this example. Does anybody have any questions about it? Because I think that this example is so fundamental not only to beams, but really the class. Because there's a lot of, behavioral related issues that are so important to what we talk about. So does anybody have any questions about this? Okay. I have one more bending topic that I would like to discuss with you, and this topic is going to be short because it's not really difficult. It's just a little bit more plug and chug, and it's about the concept of nonsymmetric bending. Now, before I get into nonsymmetric bending, I really need to take these problems and discretize them from a 2D perspective to a 3D perspective. So if you recall, when we developed our derived formula for normal stress in some element, we said it's P over A plus My over I, right? P over A being from the axial load and My over I being from the bending moment. Now, that was only for 2 dimensions, okay? Because we cut a section, we said, well, there's 3 equations of equilibrium in 2D. We've got sum of forces in the x direction, sum of forces in the y direction, and sum of moments. Now, this sum of forces in the x direction is related to shear, which we're going to talk about here in a little bit, okay? But for now, we sort of neglected that, and we said, well, there's really only, that's really all we have is axial load and moment in that perspective. But in 3 dimensions, we got a lot more than that. Now, a lot of this stuff you should be able to handle right now. For instance, we've got axial load P. What about that torsional moment, T, we've done that, right? We can handle a section subjected to a torsional moment, right? TL over GJ, remember all that? So we can handle those types of stresses and strains and deformations. We can handle stresses, strains, and deformations associated with P. But when we throw it in 3 dimensions, we're going to find there's a few terms that pop up that we might not have been familiar with. So what I'm going to do is a similar derivation to what I did last time. I might go a little faster because a lot of this I think you're going to find is fairly familiar. So what I'm going to do is I'm going to assume that I've got some arbitrary cross-section. Remember, my cross-section looks like some stressed potato, right? And I'm going to say that this arbitrary cross-section has some differential element dA. Now, if you're wondering why I got the axes flipped around, I say that's because of civil engineering sign convention, but in all honesty, it's really because if you think about it, we use the whole concept of smiley face positive, frowny face negative for our bending moments. Well, if you get into the whole right-hand rule thing, that's actually upside down. So that's why the axes are faced like this. All right. Okay. Now, let's recall the following properties so that everybody's getting back into this mode of thinking. So if I integrate over the area, the integral of dA, that's just area. That's just the area, right? If I integrate, y squared, that's the moment of inertia about the x-axis. Or if I integrate y squared, that's the moment, or if I integrate x squared, moment of inertia about the y-axis, and etc. I probably said something backwards there, but my coffee hadn't kicked in. Okay. Lastly, the centroid, sum of ax over sum of a, or the integral of x over the area divided by the area. And same thing with y bar. Sound good? Now, I'm going to introduce to you a new term, okay? If the integral of y squared is the moment of inertia about the x-axis and the integral of x squared is the moment of inertia about the y-axis, I'm going to introduce to you the following term. This is called a product of inertia. It's called IXY. So I've got the integral of x squared, I've got the integral of y squared, and I've got the integral of xy. The reason why this is going to pop up, here and there in our derivation. I just want you to see the shorthand for what I'm going to use. And really, this is the whole issue with non-symmetrical bending, is being able to compute that. Once you can compute that, non-symmetrical bending is as plug and chug as anything else. Okay, so let's go back to our assumed function. So sigma equals C1 plus C2x plus C3y. So I'm assuming that the stress is linear, but I've got to assume that linearity in both directions. So if you remember from, I don't know if it was pre-calc or calculus or whenever you took this, but if C1 plus C2x is the equation of a line, C1 plus C2x plus C3y is the equation of a plane. Okay? So I'm assuming that's sort of the stress plane about that section. Make sense? All right. All right. So this is going to be pretty straightforward. So if I'm looking at that little differential element, the force on that element is stress times the area. So the area is dA, and the stress is that C1 plus C2x plus C3y. That's the equation I've come up with. The moment about the x-axis is going to be the force times y, because how far away am I from the x-axis? I'm y away, okay? And how far away am I from the y-axis? Well, I'm x away, okay? So everybody see the difference between, like, for instance, what I got here and here? I've taken this whole thing and multiplied it by y. So C1 times y, C2x times y, C3y times y. So that's where I get the y squared. Everybody okay with that? Okay. Now, all of those that you see right there are expressions of differential forces and differential moments, just the force on that little bitty dA element. I've got to integrate, right? So if I want the force on the whole thing, I got to integrate that entire thing. So for instance, let's look at the top one. So to get the force on the whole section, I got to integrate. So I integrate my dP, which is this, C1 plus C2x plus C3y, and then go back to fundamental calculus. If I got constants, I can pull them out, and if I'm integrating a sum, it's the sum of the integrals, right? So I can just split it up into a bunch of integrals. Sound good? Okay. So we have a number of substitutions that we can make if we start paying attention to this one by one. Like, for instance, if I'm looking up here, okay? The integral of dA, that's the area, right? Since I put my coordinate axes at the centroid, this is 0. That's 0, right? Sound good? I can start doing this. Okay, so this one is 0. This is my product of inertia. That's the moment of inertia about the x-axis. Everybody see where I'm coming up with this? So I'm gonna start plugging and chugging. So what I can do is if I look at the first equation, it gets pretty simple because I've got, C1 times A plus C2 times 0 plus C3 times 0. I get that. And I can solve that and get C1 pretty easily. It's just P over A. The other two take a little bit of work. Remember that whole 2 equations and 2 unknowns problem you all dealt with when you took algebra or pre-calc or whatever it was and you had to do the elimination and whatnot? Well, that's what you got to do to solve this. It gets a little bit, well, it turns into alphabet soup kind of quickly. But what ends up happening, and I'm more than happy to go through the math with you, but to solve this, it's pretty straightforward. You get C1 as P over A. These two, you have to do the whole 2 equations and 2 unknowns scenario. And when you go through and chug it all out, you get the following expression, that C2 equals all this and C3 equals all this. No, it's nasty, but it's really just plug and chug. If you know the moments that are being applied and you know your section properties, you can calculate them pretty easily. Sound good? So when it's all said and done, there's your bending stress equation in that box there at the bottom. P over A plus that quantity in the parentheses times X plus that quantity in the parentheses times Y. In other words, if I'm looking at, some beam with some arbitrary cross-section and I want to know the stress right there, just tell me what the X and Y coordinates are. That's X, that's Y, plug and chug. And that's it. It's that simple. Okay? Anybody have any questions? It's really not that bad. The only thing that's a little new is IXY, which is that product of inertia. Okay? Now, we can use the parallel axis theorem as well. Remember the sum of I plus AD squared? Instead of doing D squared, because we're doing distances about the x-axis and distances about the y-axis, it's pretty much the same, but the format's a little different. The only thing I will point out is, when we calculate a moment of inertia, it comes out to be, like 400 inches to the fourth or 600 inches to the fourth. Because of what we're doing here, it's very possible that IXY comes out negative. So don't freak out if you get a negative number. That's okay. Now, one of the things about a product of inertia is that if anything's symmetric, you have an IXY of 0. So if you go to this, massive equation, and if you're dealing with a symmetric shape like a rectangle or an I-beam or something like that, and you plug in 0 everywhere that you see IXY, you get this, which is a whole lot simpler. And if you've only got bending about one direction, then that's the same equation we've been dealing with before. Okay? So the big point I wanted to make is that in 3 dimensions, the equation gets hairier, but if you only got one moment and you've got a symmetric shape, it goes back to the same thing we were dealing with before. All right. Any questions? All right. The only thing I'm interested in is that you all have a reasonable understanding for how to compute that product of inertia, because if you can get that, it really is plug and chug. So we're going to determine the product of inertia for the following shape, but I didn't want to take a terrible amount of time during class doing this because it really is pretty rote. So let me pull this up. So one, two, three, four, five. Oh, I can't count. That's what it is. Wait, you need one more. That's what it is. Oh, you got it. Okay. Okay. All right, so here's the algorithm, and I think you're going to find this is pretty straightforward, pretty rote. So what we've got going on is we've got this shape, and we're going to compute the product of inertia. Now, just like we've done with similar problems where we're computing the moment of inertia about the x-axis or the y-axis, we have to choose a datum. So I said, let's keep it simple. Let's say that's our datum. So this is the x-axis, this is the y-axis. Now, I'm going to split this up into two shapes, a rectangle and a triangle. Now, if I go through and do the rectangle, so this is B and that's H, so it's 10 inches wide and 8 inches tall, I can compute the area, I can compute where the centroid is. Note that I can calculate the moment of inertia about the x and y axis, just bh cubed over 12 or b cubed h over 12, but ixy is 0. Okay? Sound good?
Should your Y bar be 4 inches?
Oh, yeah, it should be. Did I do that in the table? Let me see. Yeah, you're right. Whoops, that is an error. So I'll probably have to adjust that accordingly throughout the calc. So yeah, that's 4 inches. Whoops. I think that puts me at about, what, 4 mistakes this semester? Is that about where I'm at? Something like that.
4 given problems on the exam.
That's a reasonable assumption. It's an incorrect one, but a reasonable one. All right. So you all get the drill on this evaluation. Let me erase this because that's going to like that. Okay. For the triangle, same story. We can calculate the area. We can calculate the x and y bar, which I think I got that right. Yeah, 8 cubed. Yep. Okay. The x bar again. We're going from the axis. Okay. Ix and Iy we can calculate, but we really don't need that. What we need is this, Ixy. And if you look that up, go to that appendix. I believe it's appendix E, is it? It comes out negative. So b squared h squared over 72, plug and chug, and that's what you get. So here's the long and short of it. So we have our rectangle. Here's the area. The rectangle's 80, triangle's 32, so the area is 112. Here's this and this. Yeah, that one's wrong. That should be 4, so bear with me on that. So here's our moment arms. We calculate the centroid about from the x and y axes, so there's what we get. We plug in our Ixy's. Our dx and dy's, as long as you're consistent, it's fine. So we can say for this one, that minus that and that minus that will give us the d's, and then that minus that and that minus that will give us the d's for the y direction. And then it's just that plus the area times that times that. Sum it up. That's it. There's a lot of that's there, but I think you all followed along pretty well. Any questions? D's, remember, it's the distance from the centroid of each individual component to the centroid of the whole thing. And all you've got to do is just say x bar minus x bar minus x, and then y bar minus y bar minus y. That's it. Bless you. Any questions? Pretty straightforward stuff, though. I think the algorithm's pretty direct. Okay. Everybody good? Okay. Now, any questions? All right. I need a notebook from somebody. Okay. What we're going to talk about now is shear stress. Okay? Now, we've talked about bending stresses, sigma equals my over I, but I want to go to a problem like this. Recognize that if I apply a point load to a beam, not only do I generate a bending moment, but I generate a shear as well, right? All right? We haven't accounted for that shear. Now, I borrowed Mr. Phil Singer's notebook. Why is that? Okay? If I take this notebook and I begin to bend it, it bends pretty easily. Anybody guess why it bends pretty easily? Exactly. The pieces of paper are sliding right against each other. Nothing's holding the pieces of paper together. Now imagine if I had a lot of time on my hands and I sat here and I glued together each sheet of paper. I'm not going to do that, but what's that? He would not be happy with me because he would not be able to study for the celebration coming up. But in all seriousness, what do you think would happen to the strength of this section? Be a lot stronger, okay? Because the fact that the pages are stuck together, they are going to resist load. And think, what's happening? The pages are sliding like this. They're shearing against one another, right? So we need to consider that, because in a solid beam, that is what's happening, right? You know, there you go. Right? Here's my beam, and I'm applying some load. Imagine if I took a, almost something like a deli slicer and was slicing this thing up into various slices. Along each of those planes, there's a shear stress being developed. Make sense? That shear stress changes along the depth, and we're going to see that. But it's just something I wanted to make sense. Hopefully that made sense. Okay, so for my discussion, I'm going to consider the following beam. And the reason why is because the shear is constant, but the moment isn't, right? Moment is changing. The moment is linear, okay? Now, I have got, in my humble opinion, some of the prettiest pictures in this section, so, applause would not be, unwarranted. I'm kidding. I'm kidding. I'm really kidding. Kind of. All right, so I've cut out a little differential element, my little dx slice, okay, of this beam, and I'm looking at it. Now, here's my dx slice here at the bottom, and what I'm finding is this, okay? Because of my loading conditions, regardless of if I look on the left side or the right side, I've got the same shear, right? Because the shear is constant. Whatever the value is here, it's the same value there. Sound good? But the shear is constant. That doesn't mean the moment is constant. If I look from the left side to the right side, there's a little dm, right? A little differential change in moment on the other end. Sound good? Okay. So let's look at this, okay? So here's that little differential element, and I'm looking at it in 3 dimensions. So this is that little slice. So I cut the slice out, and I pulled it out, and I'm looking at that slice. So let's diagnose what's going on here. So the little slice is dxy, okay? Now if I samurai sword or lightsaber through the section, and I look at the beam, what do I have? It's b wide, h tall. Sound good? For now, I'm keeping this restricted to a rectangular cross-section. All right? Sound good? All right, so what's this dashed line right here? What does that represent? The centroid. Okay, the centroid of that rectangle is right in the middle, right? H over 2 from the bottom or the top. So I'm saying that y goes from that centroid. So this is y equals 0. This is positive y, negative y, what have you. Sound good? Okay. Now, this is my bending stress profile, right? Now, I've got, let's say, compression on the top, tension on the bottom, right? Sound good? Same thing over here, but here's the rub. I have a bending moment over here, but I have a bending moment plus that incremental change over here. So if I got sigma equals my over here, I got sigma plus some differential change. My over I plus dm y over I. Sound good? So this would be the stress on the left side. This would be the stress on the right side. Sound good? Okay. Any questions? All right. Now, let's sort of read this out. Okay. Even if the shear is constant, we've got some incremental change in moment, because the change in moment with respect to x, dm over dx, is the shear. So there's going to be some change. Okay. That's point 1. Point 2, okay? And this is going to become clear. I don't care what's going on. The sum of forces in the x direction has to be 0, okay? I don't care what's going on. That has to maintain, okay? Sound good? We got to have that. All right. So what I'm going to do, I'm going to look at the total forces due to bending. I'm going to cut myself a little slice out, okay? And I'm going to look at a little bit of the an area of that slice. I'm going to look at the forces on that. So I'm looking at this shaded region, and it'd be the same thing over here. I'm going to say that the area of that shaded region, this blue region right here, I'm going to say that area is B times some differential thickness dy. Sound good? Okay with that? All right. Now, if I look on the left side, what's going on the left side? Well, on the left side, I can calculate the force on that strip. What is it? Sigma times dA, and I can integrate. Sound good? Now I'm integrating along that depth, which is really from here to here. So that's from y naught to h over 2. Sound good? Now, I'm saying that the forces going to the right, let's say, are positive, so these forces are going this way. These forces here are going to the left, so that's why I got a negative sign. Sound good? Any questions? All right. Now, if I substitute some stuff, so my differential element is b dy. I've got that red, so if this is a really colorful slide, bear with me. So if I look here, so the force on the left, sigma dA. So dA, that's b dy. The sigma, that's my over I. Plug and chug. Factor out all the common stuff. This is what I got. Sound good? Same thing on the right. Do the same treatment. Plug and chug, factor it out, keep everything simple. So far, so good? If sum of forces in the x direction has to be 0, I got a problem. Because if sum of forces in the x direction equals 0, and this is all I got, then the force on the left plus the force on the right has to equal 0, but that's not the case. Okay? I've got this chunk of stuff that doesn't equal 0. Okay? That's a problem. Okay? So there's got to be something else going on. There's got to be something else there. I go back to the example with the notebook. If I bend that notebook, what happens? We get shears developing. Right? There's nowhere else on this beam that we can develop stresses. You know, it's being loaded here and here. There's nothing going on the front and back. There's nothing going on the top and bottom. There's nothing there. The only place that I can develop stresses is inside. So if I cut this off and I look in here, just like the pages of that notebook that are sliding together, if I glued them, they wouldn't be. Why? Because they developed some stress. I propose that there is some shear stress acting along this plane. Make sense? Now that stress I'm going to assume is uniform. I'm going to say it's the stress over the area. What's the area? B dx. Sound good? I propose that that is the force developed by shear along that plane. Everybody good? All right. So now I've got sum of forces in the x direction, the force on the left plus the force on the right plus shear. I got something else to deal with. Now let's see what's going on. Now I think we can determine how much this shear stress needs to be so that the sum of forces equals 0. So what we got going on? Well, take this, rearrange it a little bit, and there you go. So what did I do? I took all this, brought it over here, and I divided by b dx. And here's what I got. So let's look at this for a little bit. So I got this integral. I got 1 over IB, and then I got this, dm over dx. Let's start off with this. What is dm over dx? What is that? That's the shear, right? So dm over dx, that's V. That's the shear. Okay? Sound good? This term in here, this is a section property. Okay? It is a property of that beam. Okay? Sound good? So what I'm going to do is this. I'm going to say this is shear, that's V, and then this term inside this brackets, it is a section property, just like the moment of inertia, just like J, just like all these different section properties that we've been computing, that is one as well. That is essentially a first moment of area, an area times a distance. So, we tend to call that Q in our world, Q being the first moment of area where we're trying to find that shear stress. So, lo and behold, we find our fourth fundamental stress formula. Remember, we had a stress formula for axial loads, a stress formula for torsion, a stress formula for bending, sigma equals my over I, and now we have one for shear. The shear stress that you find along the depth of a given section is V, the shear force, times Q, first moment of area, divided by I, moment of inertia, times the beam width B. Okay? So tau equals VQ over IB. Okay. Any questions? Don't worry, we'll have an example going through this. It's not so bad. Everybody good? Now, one of the reasons that I kept that example simple, or let me say this. let me say it like this. One of the reasons that I kept the example as a rectangular section is so that B would be constant, okay? There is nothing to say that B couldn't be a variable, okay? What do I mean by that? Well, here's an instance of B being a variable. So on the top is a rectangular cross-section. And what happens is this. If you plot the bending stress profile, sigma, you get that triangular stress distribution. You know, compression on the top, tension on the bottom, linear variation in between. Sound good? Now the shear stress profile, the VQ over IB, if you go through and calculate the shear stress profile and plot it, you get something that looks kind of like this. It's a parabola. I know this kind of looks a little circular, but it's really a parabola. All right, sound good?
This is effectively the same thing as a constantly, not solid load. Yeah, distributed load beam from the top.
Yeah, I don't know that the actual load on the beam really matters because we're...
In terms of moment. This looks like the moment reactor distributed load beam.
Oh, no. What we're doing is this. I see what you're saying. Okay. So what we're doing is this. Okay. We're saying, okay, here's a beam. Right? And it's got, you know, whatever loads on there, right? Load here. It does look similar. It's not the same thing, but I see where you're coming from. But it isn't. What I'm getting at is that what you were saying earlier was correct. Like I cut a cross section and I'm just looking at the shear stress and the bending moment at that section. If I zoom in, you know, right here, I've got, you know, that, and here's where I cut that section, right? I propose that we're developing a bending stress that looks like that, and we're developing a shear stress that looks like that. Now, let me say this, okay? Let me go back a little bit. Let me see if this makes any sense. And this is going to test my artistic ability, so bear with me. Okay, let's look at the shear stress profiles. If I were to look at the shear stress profile like right here, right at the very left side of the beam, you know, I would have a fairly large stress profile. Oh, that's not good. Maybe it looks something like this. All right. Let's say for the purposes of this discussion that we've got a distributed load on here. Okay? As we move toward the center of the beam, the shear gets smaller and smaller. So maybe here it's, you know, like that. Maybe here it's like that. And by the time you get here, there might not be any shear stress at all because there's no shear. Make sense? Whereas the bending stress profile, you know, here there's nothing. Here there's, you know, maybe a little bit. Here there's a little bit more. And then by the time you get here, you know, it's crazy. You see what I mean? Does that make sense? Yes, sir.
So is that physically, like, you cut a section of the beam, that's what the beam's kind of doing. You got a force that's kind of pushing it this way on the bottom.
Exactly, yes. Yes. If I look at the beam when it's deformed, okay, let's say I zoom in, it's going to look, you know, something like that, like it's bent. Okay? So let's say this is the neutral axis. So the neutral axis hasn't done anything. On the top, it's squished together. I can do better now. All right? On the bottom, it's being yanked apart. And it's linearly proportional. Does that make sense? That's a good question. Everybody good? Okay.
So in this case, is the tension away from the center?
Yeah, well, always the case. Yeah, because think, this beam is going to want to deflect something like that. So everything below the neutral axis is going to be experiencing tension. Everything above is going to be experiencing compression. This is good stuff. Anybody else? I mean, I want to make sure this stuff makes sense. Everybody good? Okay. Okay. Now, what I was going back to here is I want to look at what shear stresses look like for different sections. Now, keep in mind, here's our equation, right? Our equation is VQ over IB, okay? Now, the difference between this and this is that the B changes, okay? B is the width of the section, okay? So, like if I start at the bottom and work my way up, here I've got a really, really, really wide beam. And right here, B changes, right? Everybody see that? Well, if B suddenly changes and B suddenly gets smaller, what happens to your stresses? If B gets smaller, what happens to tau? Jumps up, right? Which is why if you look at I-beams, the bending stress is the bending stress, but the shear, there's a sudden jump right here, okay? Make sense? There's a sudden jump right there where the flange web junction is, because there's a sudden change in width, there's a sudden jump in shear stress. Largely when we design I-beams, we, if we're doing, let's say, a plate girder and a bridge, we tend to split them up into their separate components. And we design the web to resist all the shear, and we design the flanges to resist all the moment. That's a ultra simplified way of saying it, but pretty close, right? That make sense? Any questions? All right. Like when you all take steel design and we look at the shear capacity of I-beams, if you take the class, you basically say that the shear capacity of a web is the yield stress times the area, and then we end up multiplying it by 0.6. But that's another story for another day. I'll explain why when you take the class. All right. Any questions so far? Okay. This example, therefore, is the last thing on the exam. This is it. After this, we're good on the exam. Okay. So for the beam below, I want to determine what is the maximum shear stress and what is the shear stress at that section. Okay? Sound good? So we're going to determine the maximum shear stress across the board for the entire beam. And then I want to know what's the stress right here at a point 1 inches from the top of the beam. So we'll take our time with this, but I think in the end it'll be fairly straightforward. Okay. So might help if I open up my little notebook. Bless you. Oh, I opened it. I promise I did. Can you believe we've done 59 pages of this stuff? Goodness. Oh, okay, okay. I see how it is. Oh, no, I did open it. That's okay. Snarky comments aside. All right. What is going on with this machine? Okay. All right. Example 24. Okay. So the first thing I want to do is let's just look at the beam. All right. So I'm being subjected to a load right here of 4,000 pounds. Okay? Now, in terms of distances, oh, it's 6,000. Whoops. It would help if I could read my own handwriting. I know I've got problems with that, though. Never going to live it down. Nope. All right. Okay. So distances, okay, yeah, this is 4 feet, and this is 2 feet. I was looking ahead. I was looking at the dimension. Okay, so that's 4 feet, and that's 2 feet. Okay, all right. So we're going to need to develop a reaction here and here. Now, can I just go ahead and tell you the reactions, or do you want me to do it? I mean, I think by now we could probably figure out that that's 2,000 and that's 4,000. I mean, if you're still unsure, just some moments. Like if some moments at this left hinge, 6,000 times 4 has got to equal something times 6, right? And that something is 4,000. Make sense? All right. Excuse me. So, now keep in mind we do have this section right here that we've got to assess, this section 1-1. All right. All right. So we got a shear diagram. We're going to do it in pounds. So you tell me what to do when we're drawing the shear diagram. So we're starting here. What's the first thing we do? Go up 2 grand. No change. And then go down 6 grand. No change. Go up 4. Right? So our shear diagram looks something about like this. Start up. There we go. So that's 2,000. That's minus 4,000. I did that a little quick, but I think after that last homework, you all are pretty well versed on that. Everybody good? Okay. Now, let me try and answer 2 questions. First off, what is the shear at section 1-1? 2,000 pounds. Now, as for V max, it's going to be 4,000. Now you think, wait a minute. First off, a couple things. Why isn't it negative? And if you're talking about numbers, why isn't the maximum 2,000, not the negative 4? Because I'm looking at magnitudes, okay? And what is the largest magnitude shear that this section is facing? And it's 4,000. By and large, in the world of shear, while we need a correct sign convention to draw our moment diagrams, really the direction doesn't really matter for shear. In other words, an element largely behaves the same way if I'm shearing it like this or if I'm shearing it like this. It's still shear, okay? Now the compression versus tension on bending, that sometimes you need to be a little bit careful with. But all in all, the direction really doesn't matter. All right, sound good? Okay. Now before we get into part A and part B, we need some beam properties. So we have a beam that is, what is it? It's 2 inches wide and 4 inches tall. Did I get that right? All right. So help me out. What's the moment of inertia of this beam going to be? We don't need to go through and do a full-blown parallel axis theorem because it's just a rectangle, right? So what's the moment of inertia of a rectangle? BH cubed over 12, exactly. And if you don't remember, just go to Appendix E. That's a good question. The answer is yes. I'm not one of those professors that makes you want to memorize everything. And you'll definitely have this, the sections for the like the W shapes and the angles and T shapes if you need them. There's no way I'm making you write all that down. So. All right. go through and plug and chug, it comes out to about 10.67 inches to the fourth. Sound good? All right. Now, Q, okay? Q is a little, I guess, trickier, so I'll take my time with that. Q, we've actually got to derive. So here's my centroid, okay? We've got, this is our slice. Remember, that's our slice above the section that's what, dy tall or what have you. This dimension is y naught. That dimension is h over 2. And I propose that q is the integral of y naught to h over 2 of by dy. That just comes straight from our derivation, right? Plug and chug. Sound good? And so everybody clear where I got that? All right. So B is the width. I mean, the beam's always 2 inches wide, so it's B times the integral of y, which is just y squared over 2, which is evaluated from y naught to h over 2. So if you want, you can say Q is B over 2 h squared over 4 minus y naught squared. Sound good? Lastly, if I want to determine what is the shear stress, it's just VQ over IB, which is V over IB times the following. What happens to the B's? They drop out. So now I actually wanted to go through and derive this formula for us. That is the shear stress formula for a rectangle. Nudge, nudge, wink, wink, hint, hint, formula sheet for celebrations. All right? That's a good one to put on there. Sound good? All right. Any questions? All right. Everybody have all this? Or you want me to leave it up for a sec? No, it's fine. Go ahead. Everybody good? Oh, the suspense. I'm kidding. All right. Now, I want to go back to that cross section and look at that formula because I want to make some sense out of this. So part A. Now part A asked for tau max, right? The maximum shear stress across the board. Sound good? Now let's go back to that beam. Here's the beam. And our shear stress formula is V over 2I, and what is it, h squared over 4 minus y naught squared. All right, so let's just be clear and make sure we're understanding some values. So I is that, right? 10.67 inches to the fourth. We already computed that. H is 4 inches. V, in this case, we're looking at V max. £4,000. Now, can we plug and chug into this? What are we missing? Y is 0, right? Sound good? All right, so let's do a little bit of figuring, okay? Y0, let's look at this equation. I'm going to take V over 2I times this quantity, h squared over 4 minus this. So if I want to get the maximum shear stress possible, what value should I plug in for Y0? Okay, what happens if I plug in h over 2? Well, if I plug in h over 2, it would be V over 2I, h squared over 4 minus h over 2 squared. So that'd be V over 2I, h squared over 4 minus h squared over 4. So what is that? That's not going to give us the maximum shear stress. That's what we're trying to find, the worst case shear stress imaginable. So what value of Y naught should I plug in? 0. Now think, where is Y naught measured from? From the centroid. Make sense? I propose that the worst shear stress location we're going to get is right in the middle. Go back to this. What does your shear stress profile look like? It looks like this. There's your worst case shear stress, right? Right there. And since Y naught is measured from the centroid, tau max, I'll do this over here, tau max occurs at Y naught equals 0. In other words, the middle of the beam. Yes, sir?
So the graph, that's like the Z shape, that's just regular stress.
Yeah, that's bending stress. This is shear stress. Yeah, that's a really good point to make. When we're talking about bending stress, the worst case bending stress is either on the way, way, way tippy top of the section or the way bottom. Worst case shear stress for this rectangular section is in the middle. Make sense? Not too bad, right? So I propose then that tau max is V over 2I times h squared over 4, which is VH squared over 8I. So what's that come out to be? What's that? Little less than 800. Yeah, there you go. It actually, if you carry out your decimals on that bottom, comes out to exactly 750. Isn't too bad, is it? All right. Now, let's look at part B. I want you to read part B for me. Let's read that out. What does it say? Or the second part. The stress at the section. So let's start off with that. What was the shear at that section? Remember that section 1-1? There we go. Part B. V was 2,000 pounds. Whoop. All right. And what else does it say? The stress at that section where? What does it say there? So at a point 1 inches from the top of the beam. So let's look at this. How tall is this beam? 4 inches. So this right here, this h over 2, that's what? 2 inches. So if we're talking about a point 1 inches from the top, what's y naught going to be? What would you say? Inch over 4? Hold on. I think we're thinking too much about this. Let's look at this. All right. So here's our beam. Here's the centroid. Here's our slice. And this is y naught. All right? Now, help me out. What is this dimension right here? The numbers. 2 inches. All right? Now, when we determine shear stress, we're determining shear stress at this solid line right here. Okay? Now, it's set a point, how far from the top? 1 inch. So, if this dimension is 1 inch, what is y naught? Simple, right? Is everybody okay with that? I'm serious. This is important. Is everybody okay with that? What's the problem say? Let's go back to the problem. All right, so we're determining the maximum shear stress, and then right here, the stress at the section, right here, and then determine tau at a point 1 inches from the top of the section. Sound good? You all have a homework problem where you're going to determine stresses at various different slices along the section. I think it's your last one, so you'll want to make sure you know that. Sound good? Everybody good? All right. So, we've got, here's our equation. Plug and chug. Right? What do you get? Oh, wait. I messed something up. That is 2,000. Okay, hold on. First off, that's supposed to be tau, not tau max. And what'd you get? 0? I was to say, that sounds about right. 281 point, yeah. I got 2.5, but it doesn't matter.
I'm just trying to do it.
Oh, that's the problem right there. That is, that's even more mistakes today. That's 4 inches. Whoops. Yeah. No. Follow that out. Follow that out. Yeah, we're looking at the distance from the centroid to the slice. And if this is 4 inches, that's 2 inches. If this is 2 inches coming down 1, that makes that 1. Did anybody else get this? All right. All right. Does anybody have any questions? How's everybody feeling about this stuff? Feeling good? Test 2 stops right now. Any questions? All right. Now, my structural analysis folks, if they were thinking that this stuff bled over from one class to another, they certainly are going to feel that way now. We're not going to do this today because we're running out of time, but there's one final topic that's left in beams that we haven't covered, and that is deflection. I take a beam, I apply a load, it bends, it deforms some amount. And since I was looking at the college catalog and it said that this course is mechanics of deformable bodies, I thought maybe we should talk about the deformation. That was a joke, not a very funny one. What we're going to do is talk about the equations that govern beam deflection next. Now there's a litany of methods that you can use to do beam deflection. I'm going to show you 2. One of them is going to be double integration, which is just taking the equations and directly integrating them. And the second is what's going to be called superposition. In other words, it's easy to derive beam deflection equations for simple cases, and if you've got complex loading cases, just sum them up, okay? So that's going to be our 2 methods for beam deflection. Now that's sort of a topic off to the side. The big chunk for the rest of the semester is going to be combined loading. In other words, you all know how to handle a bar that is being yanked on. You know how to handle a bar that's being twisted. Well, what if it's being yanked on and twisted? What if it's being yanked on and twisted and bent and sheared? Multiple stresses acting on a section all at once. Okay? How do you handle multiple stresses at once? That's combined loading. Okay? We handle that through a tool called Moore's circle. And we will deal with Moore's circle for the later part of the semester. After that, we've got column buckling, and that being mechanics of deformable bodies. So with that, that's everything on exam 2. I'm going to call it now. Y'all have a good one, good weekend. We'll see you next week.